in this video we're going to start our conversation about bonding in organic chemistry. So when it comes to organic chemistry, unlike in general chemistry, we're not going to look at the entire periodic table out there, we're just going to look at a few core elements. And if I ask you which is the core element of organic chemistry, you're probably going to be like, duh, that's our carbon, of course. However, in addition to carbon, we're going to have a few other elements. So let's look at our periodic table. At the very top of our periodic table, we see hydrogen. Then, when we move to the next period, we're going to have lithium, beryllium, boron, then we have our carbon, then we have nitrogen, oxygen, fluorine. We also have chlorine, bromine, and iodine. In the third period, we're also going to see silicon, phosphorus, sulfur, then we have arsenic and selenium, and finally tellurium right next to the iodine. Now, this is what I would call a relevant periodic table of organic chemistry, because these are all our non-metals, well, except for lithium and beryllium, of course. And these are the most typical elements that we are going to see within the scope of organic chemistry and within organic molecules. Of course, the core of organic molecules is going to be carbon and hydrogen. But in addition to that, we're also going to have two main support elements. And those support elements are going to be nitrogen and oxygen. They're going to be very frequently showing up in our molecules, and we are going to see them quite often. In addition to that, we're also going to see our halogens, chlorine, bromine, and iodine. Then, on a rare occasion, we're going to see boron, phosphorus and sulfur, fluorine, and maybe an occasional silicon here or there, although we are not going to go too deeply into the chemistry of any of those elements, maybe sulfur to some extent. The rest of our elements, like arsenic, selenium, tellurium, well, unless you really want to see some fancy chemistry that goes beyond the scope of a regular sophomore organic chemistry, then you are going to see some of those guys. When it comes to metals, most metals, especially the alkali metals like lithium or sodium or potassium, those ones are going to be majorly irrelevant within the scope of our course. Not that we completely going to skip those. No, they're going to be relevant in the sense that they're just going to be spectator ions. They're just going to be bearing the positive charge, and within the scope of this course, we're not really going to be looking too deep into what exactly they do with molecules and how exactly they participate in different molecular entities and how exactly they change the behavior of organic molecules. That typically goes beyond the scope of a sophomore course. However, some instructors do point that out, so when it comes relevant, we are going to talk about that as well. Now, in addition to the position of the elements in the periodic table, there are a couple of other things that is going to be relevant to us. And probably the most relevant thing is going to be the group in which our elements are located. Groups are the vertical lines, the columns, if you like, of our elements. The first group is hydrogen, the second group is the one where we have beryllium, then we have the third one with the boron, fourth with the carbon, then nitrogen, phosphorus is group number 5, oxygen and sulfur is group number 6, and we have halogens in group number 7. And of course we have group number 8 with the noble gases, but we don't really care about noble gases, they don't participate in any relevant chemistry to us, so I'm pretty much going to forget about their existence for right now. So, why the group is so important for me? Well, the group number, so here I have my group number, that number relates to the number of the valence electrons that the element has. And if we know the number of the valence electrons, we can always easily figure out the Lewis structure, and from the Lewis structure we can figure out the chemical properties of the elements, etc. The second important bit of information that we have from periodic table is the period. We have the first period for hydrogen, then the second period for the second row of elements. So periods are the rows of our elements. Then we have third period, fourth period, and tellurium and iodine are in the fifth period. So that is my period. Now, The relevance of the period for right now is going to be relatively small. Later on, when we start talking about the stability of our molecules when they are bearing charges, depending whether it's going to be positive or a negative charge, the period becomes extremely relevant because as we go down in the periodic table, the elements become bigger and bigger. The size grows, the elements become larger, which means that size is going to start playing an extremely important role in the orbital size, and orbital size become more relevant when it comes to stability of electrons, etc. But for right now, period is just a cute number on the left side of our periodic table, so let's not focus on that too much. The most important part for us is the valence electrons that we are going to grab from the periodic table, from the group where the elements are located. Now, the reason why the group is so important and the number of valence electrons is so important for us, because if we know the number of the valence electrons, we can easily predict how many bonds each element can make. So if we look at hydrogen, well, hydrogen is sitting in the first group of the periodic table, which means that hydrogen can only have one bond because it has one valence electron. If I move along to, let's say, boron, if you look at your periodic table, you will see that boron is already in the third group, so it has 1, 2, 3 electrons, which means that boron can easily make 3 bonds. Next, let's say we look at the carbon. Carbon has 4 valence electrons because it is sitting in the fourth group in the periodic table, so we have 1, 2, 3, and 4 electrons over here. Then, moving along our period, we have nitrogen. Nitrogen is in the fifth group, so it has 5 electrons. But here is something interesting. Once we reach our fourth electron, we're going to start pairing the electrons up, so nitrogen is going to have 3 single electrons and a pair of electrons. And that is very relevant to us because when we have single electrons, those guys can make bonds, so nitrogen can make 3 bonds. But the electron pair cannot participate in bonding to make neutral molecules or neutral atoms. It can definitely participate in bonding, but if we are going to be using our electron pairs for bonding, then we are going to start making charged atoms. And for right now, we just want to keep to neutral atoms. Next, if we move to the oxygen, oxygen has 1, 2, 3, 4, 5, 6 electrons. So in the case of oxygen, I have 2 unpaired electrons that will be able to give me bonds, and I have 2 paired electrons. Thus, oxygen will be able to make 2 bonds. And finally, if we look at halogens, let's say I have chlorine over here. Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons. So chlorine will be able to make 1 bond, and the other 3 electron pairs that we have around chlorine are just going to be hanging out there, not participating in any bonding for as long as chlorine is neutral. So going back to my elements on the left side here, I can say that carbon can make 4 bonds, boron can make 3 bonds, and hydrogen can only make 1 bond. For the simplicity's sake, whenever we are drawing our molecules, however, whenever we have a bond, we are going to represent bond with a line. So if I have 2 hydrogen atoms participating in the bonding, then when those 2 atoms come together and make a bond, we're going to have a pair of electrons between those atoms. However, drawing those endless dots is going to be a little bit tedious, so instead, what we're going to do, we will represent that bond as a line between the hydrogens in this case. So remember that whenever we have a line, that always represents a pair of electrons bonding 2 elements together. So if I have, let's say, 1 hydrogen, 1 carbon, and let's say we add a few more hydrogens over here to make a methane molecule, then what I'm going to end up with is H, 2 electrons to carbon, 2 electrons to another hydrogen, 2 electrons to another hydrogen, and 2 electrons to another hydrogen. Again, drawing something like that is quite tedious. So instead, what we're going to do, we're just going to show lines between our carbon and hydrogens to make a final molecule looking like that. So when it comes to Lewis structures, they are the most basic method of representing of organic molecules. And of course, we don't have Lewis structures just for atoms, we can draw them for different molecules. And in order to make the molecular structures come easy, we're going to use the basic building blocks. And those building blocks come from the Lewis dot structures. So I'm going to remind you that hydrogen building block is going to be H with 1 bond. The carbon building block is going to be carbon with 4 bonds. Nitrogen building block is going to be nitrogen with 3 bonds and an electron pair. And oxygen building block is going to be 2 bonds, 2 electron pairs, and finally halogen, let's say a chlorine, is going to have 1 bond, and we're going to have 3 electron pairs like that. So using these building blocks, we can easily construct pretty much any kind of molecule that we have in front of us. So let's look at something fairly simple. It's going to be CH4O. Well, in this molecule, I have a carbon, so my building block for the carbon is going to be carbon with 4 bonds. I have 4 hydrogens, so I have 1 hydrogen, 2nd hydrogen, 3rd hydrogen, and 4th hydrogen. And finally, I have an oxygen atom, so the building block for the oxygen is going to be O with 2 lines and 2 electron pairs. The only way how I can arrange those elements all around each other is if I put a carbon atom in the middle, then I will have 4 bonds to it. I will have hydrogen, 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 then an oxygen atom, and finally one more hydrogen connected to the oxygen, and of course oxygen has a couple of electron pairs that I'm going to show here as well. So that is going to make me a full Lewis structure of my molecule here. If I go with something a little bit more complicated with, let's say, I have 2 carbons, 6 hydrogens and 1 oxygen, then the process is going to be the same. I first note that I have 2 building blocks that are carbons. I have 6 building blocks that are my hydrogens. And I have 1 building block that is my oxygen. So in this case, there are a couple of different ways how I can build this molecule together. The first one is going to be if I put my carbons in a chain like that and then add oxygen to the end of this chain, and now all the bonds that do not have any connections to any elements, I can just finish those off by showing hydrogens at the end of each of those bonds. That gives me 6 hydrogens, and I'm going to end up with a complete Lewis structure for the molecule. However, this is not the only way how I can build this molecule. I can have a different structure where I have carbon connected to oxygen, which is then in turn connected to another carbon. So in this case, if I add all the missing bonds and electron pairs, I will have a skeleton looking like this. So adding my hydrogens to it, going to give me the final molecule like that. So molecule number 1 over here and molecule number 2 over here, as you can see, are 2 completely different molecules. And this is a very important distinction of organic molecules from the inorganic ones and from the stuff that you have seen in general chemistry, because the molecular formula that I have over here gives me absolutely no information in terms of what exactly I have in front of me. If in general chemistry I gave you H2SO4, you would instantly know that this is a sulfuric acid. But if I give you C2H6O, you have no idea what it is, because it can be molecule number 1, which is the ethyl alcohol, or it can be molecule number 2, which is dimethyl ether. Those are different molecules with different physical and chemical properties, and because of that, when it comes to molecules in organic chemistry, we're never going to be using the molecular formulas, but instead we're going to use structures. So get used to the fact that the molecular formulas is going to be something from the past that we're never going to come back to. We're always going to be showing structures, either Lewis structures or condensed Lewis structures where we show less bonds, or even bond line structures, which is something that we are going to talk a little bit later about. Now, before we wrap it up for this video, let's talk about one more example. I have C3H9N. So in this case, again, if I wanted to build all possible structures, I would have to build using my building blocks. I have 3 carbons, I have 9 hydrogens, and I have 1 nitrogen that I can use here to build my molecule. Now, in order to build the molecule, I will always start with the basic skeleton. So let's say for the beginning, I'm going to have 3 carbons in a row, and I'm going to attach nitrogen to one of those carbons at the end. I will add all of my missing bonds and electron pairs, and now all the bonds that are not connected to anything else going to be capped with hydrogens. I have 3, 4, 5, 6, 7, 8, and 9 hydrogens, so I have a full structure for this molecule now. I can also have nitrogen sitting somewhere else in my molecule. So let's say I'm going to go with the structure where I have 2 carbons in a row, then I'm going to have a nitrogen, and then I'm going to have another carbon. Adding all the missing bonds and electron pairs is going to give me a skeleton like this. Now adding all the missing hydrogens at the end of each bond going to give me the final structure, which is going to look something like this. Now pause this video and try to see how many more structures you can come up with, and then once you have your result, resume the video and we'll talk about that as well. You've got your result? So, for the molecular formula C3H9N, we can have 1, 2, 3, 4 different molecules. Maybe you have more on your piece of paper, but look closely at how exactly the atoms are connected. Chances are, if you have more molecules, it means that you have a repeat of one of the existing ones, of the one that I have here on the screen, but it's just rotated in space somehow. In the next video, we're going to talk more about the different structures that we are going to make from the molecular formulas, and all of those different structures, they're called constitutional or structural isomers. So for the next video, make sure that you have plenty of paper because we are going to be doing a lot of practice. And of course, let me know in the comments below if you got all the 4 structures here and if you have any questions, and I will see you next time.